Okay, here we go again. So this specific heat or a thermochemistry question. So what I need to know is that Q equals M times C times delta T. Also on the back of your periodic table, along with the specific heat of water if I need it. Okay, so they've given me, let's just look at what they've given me. They've given me 15.75 grams, so that looks like a mass. And they've given me 1,086.75 joules, so that looks like a Q. And they've given me a temperature change, 25 to 175, that looks like 150 degrees of change. If I subtract 25 from 175, that's 150. So it looks like I'm trying to find C here. So the way I do this is there's two ways. I can do 1,086.75 divided by, oh, clear. No, what is that? What is that business? Second, quit. Okay. Oh, let's try this again. 1,086.75 divided by parentheses 15.75 times 150 equals 0.46. So C equals 0.46 joules per gram degree centigrade. That's it. That's my answer. All I did was divide this by this and this multiplied times each other. I divided this by that and that multiplied times each other. All right, let's do another one. Okay, so let's see what they've given me. They've given me 24 grams, so it looks like I have another C again. Specific heat. Oh, they've given me a specific heat. So I have times 1.82 joules per gram degree centigrade. And they've given me a temp change, so 25 degrees. If I subtract 65 from 90, that's 25 degrees. And then I just have to multiply all those up. That's pretty easy. 24 times 1.82 times 25 equals 1,092 joules. By the way, if I make any mistakes on this, please do not send a remind to me that I made a mistake. Just know that you are a better chemist than me on that one problem. Okay. Or it might be that I'm tired and I'm just not. Okay. Okay, so first of all, I'm going to draw a heating curve here. And I'm going to label it A, B, C, D, E. And then I'm going to put 100 degrees here because I'm going to say this is the heating curve for water. 0 degrees here. Second of all, I'm going to come down here to 32 and 33, and I'm going to wipe those off the face of the planet because I really don't care about kinetic and potential energy in a heating curve. If you do, more power to you. But I don't, and no one in all my chemistry degree did either. So as you move from A to E, what is happening to temperature? It is going up. Is this endo or exo? So if I'm adding temperature in, I'm adding temp in, and I'm adding energy in, and the temperature is going up, that is endo. So as I go up the heating curve, it is endo. And as I go down a heating curve, it is exo. I'm having to take heat out of the system to make water turn into ice. As you move from D to A, temperature is going down. And this is exo, as I just said. What is happening at 5 degrees and 15 degrees Celsius? Well, in between at 5 and 15, all I'm doing is I'm adding heat and temp is going up. Temperature is rising. Oh, I could have put that over here. And temp is going up. There, adding heat and temp is going up. Rising, that's an arrow. Hope you can see that. Okay, what state of matter is at letter C? So at letter C, that looks like a liquid. At letter A, that looks like a solid. At letter E, that looks like a gas. As you move from A to E, what is... Oh! Okay, anytime now. Whenever you'd like to work. Yeah, we'll just sit here in the dark. Don't worry about my students or YouTube or anything like that, because they don't care how long these videos. Oh, mother of mercy. I will give anybody 100 points on a quiz if you can make this thing stop doing it. Okay, what is happening from A to E? What is happening to energy? Well, from A to E, energy is going up. From E to A, energy is going down. Okay, great. 36 through 7. Which chart represents an exothermic process? Well, basically, my products are going to have a lower energy than my reactants because I'm going to give off energy as heat. So I only see one where my products are lower than my reactants. That is B. Which chart represents a slower chemical process? Well, the longer the hill, the bigger the hill I have to get over, the slower the reaction, basically. So if I have a little tiny hill, it can get going fast. If I have a big old hill to get up, it's going to be slow. So chart A, which is endothermic. Endo, exo, you better know that by now. According to collision theory, what 3 criteria must be met to make products? Okay, well, first let's make that 2, since that's what we talked about in the notes. And 1 is correct orientation. And 1 is correct amount of energy. All right, it looks like we are almost there, guys. All right, which letter on the graph represents reactants? Well, we always start with reactants and go to products, and this is time. I hate that they didn't actually give you the whole chart, and this is Gibbs free energy. We can just call it energy, though. Which letter on the graph represents reactants? X. Which letter on the graph represents products? Z. Which letter on the graph represents activation energy? The one that's left. Y. You better know this guy. You better know that it's the amount of energy that I have to get over, the hill I have to get over to get this reaction started. So it starts at reactants, and it goes up to the top of the hill. Okay. Is heat being absorbed or released? Well, my products are lower than my reactants. That means it had to get rid of that energy somewhere. So this is exothermic, so it is released. Will the solution get warmer or colder? Well, if heat is being released, take a stab at what's happening. Is the graph exo or endo? It is exo. We just established that. How do you know? In other words, how can you say reactants potential energy higher than products? Well, that's one way to state it. Or you could say that you started at a higher energy level, ended up at a lower energy level, therefore that energy had to come out somewhere, and it comes out in heat. Heat. Whereas if I have a lower reactant and higher products, I had to get that energy from somewhere, so heat had to go into. Okay. Draw the opposing energy graph on, for instance, if you stated that the graph above is exothermic, draw endothermic. Oh, I just did that. I'm sorry. That's an endothermic graph. Yeah. Do I need to, let's label some stuff. Activation energy. It goes from my reactants to the top of my hill. So I have A, reactants, B, products, C, or E sub A, activation energy. D, I have the activated complex. And this would be the delta H. And delta H would be positive because it's always reactants minus products. So if this energy was 20 and this energy was 5, 20 minus 5 is 15. That's a positive delta H, endothermic. All right, guys. I know that this was quick, and I know that the first part was kind of scattered, and I know that I had a hissy fit in the first video, but man, I'm just getting tired of the lights going out on me. If you have any questions, don't hesitate to hit me up on Remind, although I'll ask you point blank why you didn't ask me the questions in class. Yeah, I'm talking to you. Ooh, black crap stuff all over my fingers. And tomorrow morning I'll be here at 6 a.m. So if you get here super early, I can answer any questions you have as well. Other than that, I hope everybody's going to do okay on this test. It's a good, basically a good pre-test to tell you how you're going to do on the final. This is a good kind of, gives you a good idea about what you're going to do. All right, guys. See ya.